You may at this point be wondering to yourself if there are any reagents that add water in an anti-Markovnikov fashion, which is to say opposite of the normal way, or also because the oxymercuration and the bromine type reactions attacked in an anti-like fashion. They come always from the backside. You may be wondering if there's stuff that attacks in a syn-like fashion. And of course, I'm about to show you reagents that do both, and they are in fact the same reagent. So, are there things that add in an anti-Markovnikov fashion? Sure. If you try to add water to a generic double bond by using sulfuric acid and water, you will always get the Markovnikov product. If you use mercury and then do the reduction, again, you will get the Markovnikov product. But if you do hydroboration followed by oxidation, you will always end up getting the anti-Markovnikov product. What you get is the result of adding water to the other side of the double bond. You don't add it at the internal, more stable carbocation position, you add it instead at the far end. And that's because we don't go through a carbocation at all. This is going to be another one of those cases where we have a step that I want to describe fairly fully and precisely, and another step that involves some magic. And again, I'm going to talk a little bit about the magic, but not in detail. So what we have is a double bond. We will then add hydroboration. We will do that. We will add borane across this double bond. Then the second step is there to remove the boron that's left behind. But the reason why we do it first and foremost is because we want to have an anti-Markovnikov-like addition of water. And this happens via a different mechanism. If we went through a carbocation, we would get Markovnikov. That's because that's the mechanism that's operative. So the fact that we're going anti-Markovnikov suggests we're going through a different mechanism. In fact, we're going through a mechanism where both hydrogen and boron are delivered at the same time and from the same side of the double bond. What we're going to do is to take this material, add borane in the first step, which leads to an anti-Markovnikov addition of hydrogen and boron, and then we're going to, in a second step, oxidize the boron off. So you might see that written as brackets ox for oxidation. Hydrogen peroxide, water, and sodium hydroxide are the reagents typically that we use for this, and in fact we usually end up heating this too, but we essentially beat on the molecule to make the boron go away and replace it with an oxygen. So the mechanism is going to be totally different. In the first case, oxygen is not a nucleophile. Oxygen replaces the boron. And in this second case, what we're doing is we're putting a boron on the anti-Markovnikov spot. There is no carbocation in this mechanism. This, once again, will be a magical second step, but before we proceed, you really need to go back and watch the borane borohydride magic video, wherein I didn't actually describe how sodium borohydride works to reduce a carbon-mercury bond, but I did describe that boron has an empty orbital on it. Boron always has an empty orbital where it can put extra electron density. It is Lewis acidic. But as soon as you attack that orbital, you are creating delta minus elsewhere in the molecule. So basically, this will come and sit near a double bond, and what happens is this double bond will nucleophilically add to that boron empty orbital. It will push electron density into that empty orbital. But as you do that, you tend to make boron delta minus. You make it relatively reactive in a nucleophilic sense. You make it unhappy. Again, watch that video for the details. But what that will cause to happen simultaneously, all of this happens at the same time and from the same side. The boron-hydrogen bond, which is now nucleophilic, which is now H minus essentially, will go ahead and add. So the result is that you add both at the same time and from the same side. This will not be an equilibrium step. This is simply downhill all the way. So hydrogen has now been added to the one side. Boron has now been added to the other side. Incidentally, this boron that I drew originally had 2 hydrogens on it. The boron that I drew originally had 3 hydrogens on it. But the result of this first step is to now have a boron that is bound with 2 hydrogens and an R group. So once it has done its addition, we now have an R group on the boron. However, if you look at this boron, you can see that it only has 3 things bound on it, which means that this boron must be ready to go again. And in fact, that's true. 2. The only difference is now, rather than having 2 hydrogens as well as the BH that's going to react, we now have the BH that's going to react, 1 hydrogen and 1 big R group. Said another way, this thing can be an R group on this boron. So then the boron comes near another double bond and another reaction takes place, and then what that does is now change one of these groups into, again, another one of these extended chains. And we now have 1 H remaining, so that means that we can come back and do it again. This boron now has 2 R groups on it, and the H is now left and it reacts further until finally the end result is that we have now reacted the boron 3 times with the double bond, and that's what happens. So if you use BH3, each boron will end up delivering 3 different hydrides to the double bond, and you end up with this material that is now completely saturated like this. So why does this deliver the reagent in an anti-Markovnikov-like fashion? Well, it's actually relatively hard to see when BH3 is doing the original attack. But by the time we have now done 2 reactions and we have 2 R groups on this boron, then it starts being a lot easier to see. The boron side of this molecule is getting dramatically larger. Whatever these R groups are significantly larger than the hydrogen. And likewise, if you're looking at this reagent right here, the alkene side, you have a terminal end, which is relatively small, and an internal end, which is relatively big. So this is really governed by size more than anything else. Sterics. The boron is the big end, and you want the big end out over the little end. You want the little end of the boron reagent over the big end of the alkene. So that's what organizes this. The boron side is relatively large, will be over the relatively small part of the double bond. The hydrogen side is relatively small, it will be over the larger side of the double bond. And that's why you get the anti-Markovnikov addition. Of course, you may recognize that some of your material will be less selective, and that's why we eventually have other boron reagents. One boron reagent that you will see drawn is 9BBN, which is a fairly strange looking molecule. And there are other reagents like that. You may see, for instance, borane reagents described in handouts that look essentially like this. And the idea is, if you want to have a single important hydrogen that's doing the reaction, then all of the other stuff that's there doesn't necessarily matter, and what you want is for it to be as large as possible for this to be as selective as possible. Really, if you're using a reagent that's other than BH3, what you're doing is making one end of the boron really, really big so that you get more selectivity in the first place. Hydroboration, oxidation, 2-step sequence.